For question 1, such drums are often used for temporary storage of gases. The inlet and outlet molar flow rates are Qi and Q respectively. So for these questions, we are required to develop the dynamic and steady state models of the system. So from the questions, we are given Qi and Q, which are equal to our molar flow rate, and this is our such drum with pressure P. So before we can solve the questions, we need to draw our schematic diagram. So this is our such drum with inlet Qi and outlet Q. And before we can perform our calculation, we need to have some assumption. So the first one, volume of such drum is constant. The ideal gas law PV equal to nRT is being used because our inlet is actually a gas. Temperature of inlet and outlet are the same. So now we need to perform total mass balance. So we need to perform total mass balance because we're given Qi, which is the molar flow rate. So the m over dt, the m here refers to the mass. So mass is equal to rho v, equal to Qi m minus Qm. The m over here refers to the molecular weight of gas, and Qi and Q are molar flow rate. We can now use our ideal gas law PV equal to nRT, and we can convert these equations into Pm minus equal to RT. So from that we can obtain rho. Rho equal to Pm over RT, and now we can substitute it into equation 1. Okay, from that we get this dPm over RT, which is our rho, times V over dt equal to Qim minus Qm. So mv over rt are taken out from the differential term because they are actually constant. V is assumed to be a constant at the very beginning. And we can actually cancel out n on the left hand side and m on the right hand side of the equation. Okay, from that we can get our dynamic model, where dp over dt equal to Qi minus Q times rt over V. So for the steady state model, the differential term is 0 and is equal to Qi bar minus Q bar times RT over V, where the Qi bar and Q bar are the molar flow rate in steady state.
Hi, now sir, just let's move on to question 2. So for all the information given in question 2, we can simplify in a schematic diagram. So the constant whole arc volume is 46 meter cubes, and then the information also gives that the flow rate and the concentration of the component A at the steady state is 2.4 meter cube per minute and 8.01 kmol per meter cube respectively. Please be careful that the concentration at steady state is labeled as CAI bar. It's not CA bar, because later we solve the dynamic models and we solve until we get a steady state, there will be two terms, which is the CA bar and the CAI bar. And the question they always give us the information at the initial steady state concentration. So that is the CAI bar. Be note of that. Also, we are also tell that the process is carried out at a temperature of 350 Kelvin and is maintained at that temperature for the whole process. Be careful that this is not the isothermal process, because later when we solve the rate constant, we find out that it's equal to Kca something. For the isothermal process, the K is a function of the pre-exponential factor and the exponential term, which is a temperature. For isothermal case, the Kca we don't have to linearize it because the temperature is constant. But for this case, the temperature is a variable. You just say that it's maintained at 350 Kelvin. So that when we solve the dynamic model, the Kca, we need to linearize the term K and Ca because it's a multiplication. So now let's solve the process, the problem. The feed extension is made. First is the perfect mixing, which means that the concentration of the air inside the tank is the same as the concentration outside the tank. And the second one is the incompressible liquid. The density is a constant. And the third one is a real constant, as just see in the question. And the final one is what I said just now, temperature is a variable. It can be adjusted but maintained at 350 Kelvin for the process. So solve for the first question, which is the total mass balance. You will solve this first, which is the dm over dt equal to the density times the flow rate in minus density flow rate out. Because you say it's a constant density and n equal to density times volume, so we can cancel out the density term and just become the rate of change of volume dV over dt. And since we say the volume is a constant whole arc, that means the volume will not change, it becomes 0. So that means also Qi equal to Q, which later when we have a lot of terms of Qi and Q, you can just make it become Q only. The next one is solve the component balance A. So for the mass balance of the A, we can say that is the rate of the change of the concentration, the Ca times V over dt, is equal to the flow rate into the inlet concentration minus the flow rate out the outlet concentration, and also the rate of the reaction happen inside the tank, because A will constantly change become B, and then the reaction A will decreasing, so negative sign. And then for the dCAV over dt term, we use the product rule to differentiate it becomes V dCA over dt plus Ca dV over dt. And then the rate of reaction, like we said just now, the I can expect become the Kca, which the rate constant will become the pre-exponential factor and the exponential term. And then we say that it's a constant volume whole arc, so we cancel the term of dV over dt, and we left only the V times dCA over dt. Finally, when we shift the volume to another side, it becomes the component balance equations, which dCA over dt equal to another term. So now, because temperature is a variable and concentration is also a variable, so when the two multiply together, we need to linearize it first before we solve to get the dynamic model and the steady state model. So this term, the linearize, after we linearize it, based on the formula that we learned in the lecture notes, the exponent to the power of activation energy over RTCA, it becomes a steady state term, and then when we partially differentiate it with respect to concentration A, and also partially differentiate with respect to temperature. And then finally, we can solve the linearized term, and we put back into component balance equation, it will solve and get the dynamic model for this term, the whole term. Then when we state steady state model, all the variable will have a bar above the variable. It will become only this term, which the exponent to the power of activation energy over the RT is cancelled. After that, then dimension variable form is also pretty easy. You just use the dynamic model minus the steady state, and those with the Ca negative Ca bar, it becomes a prime. For example, it's like this, dCA over dt, so we also solve it and get the derivation variable form. The next one is to solve the derivation variable equation. So with all the information we have just now, we actually can substitute inside the term and find out the dynamic model equation already, dV equation, dV. But the problem is we don't have the Ca bar in the derivation form. That's why we have the information of Ci bar 8.01 kmol per meter cube. We need to substitute inside the steady state model with all the information given the temperature, volume, and then the concentration, temperature, volumes, flow rate, and then we can find out the Ci bar. Please note that the Q, the flow rate, since we see is a constant, so the flow rate of is equal to the steady state flow rate, which is 2.4 meter cube. And then after that, we find out and solve, it becomes the Ca bar 0.3205 kmol per meter cubes. And we put inside the dV equation again with all the variable. Now we all have the value already. Substitute inside and we solve everything, and finally we get this dynamic model equation. Thank you.
Right. Question 3 says that a processed liquid is continuously fed into a perfectly mixed tank in which it is heated by a coil of condensing steam. The feed rate is 25,000 kg per hour of the liquid with a constant density of 800 kg per meter cube and heat capacity of 0.5. The holdup in the tank is constant at 2080 kg of the liquid. The inlet feed temperature is 30 degrees Celsius. The saturated steam is available at 150 degrees Celsius to heat up the processed liquid. At initial steady state, the tank temperature is 90 degrees Celsius. So this question asks us to derive a mathematical model of the system. Hereby, I have highlighted all the important points where we need to use this for our further derivation. Okay, step 1 is to sketch a schematic diagram. And this is our inlet stream, this is our outlet stream, this is the coil to heat up the water, and this is the stirrer, since it's a perfect mixing. I've stated here all the important points that I highlighted earlier in the question. Next, we need to list down all the assumptions. First, we assume that it's a perfect mixing. Then, internal energy can be approximated by enthalpy because of the liquid. The density, specific heat capacity of the liquid, and volume of the tank are assumed to be constant. Then, the heat losses are negligible. Move on to the mass balance. The general term of the mass balance is accumulation equals to in minus R. So we use the differential term as d rho v over dt equals to wi minus w. Since density is constant, so we keep the density outside. So dv over dt equals to wi minus w. In the question, they use the term of constant hold-up, which means the constant volume. So dv over dt is assumed to be 0. Thus, wi equals to w. Next, we move on to the energy balance. According to the assumption, we assume that for liquid system, du over dt is approximated dH over dt. So dH over dt equals to wi hi minus wh plus q. This differential term is further being expanded into d rho v cp, these are all the constant term, times with t minus t reference over dt equals to wi cp ti minus t reference minus w cp t minus t ref plus q. Since rho, v and cp are the constant terms, so we kept it outside, and the differential term will be d t minus t reference over dt equals to wi cp ti minus t reference minus wcp t minus t reference plus q. From the mass balance derivation, we derive that wi equals to w, and we substitute this term into this. So this rho vcp dt minus t reference over dt will be equals to w, since we substitute by w, so wcp, where this and this will be the same, thus we use it as a constant term, that's why we kept it outside. So wcp in bracket ti minus t reference minus t, minus and minus will become plus t ref plus q. Thus this term stays, so rho vcp dt minus t reference over dt equals to wcp ti minus t plus q. Next, we have to divide this whole term by this constant. So d capital T over dt equals to wcp over, these are the constant term, density, volume and heat capacity, so times by ti minus t plus the same thing over here where the q divided by the constant term, which is density, volume and heat capacity. Thus this will become d capital T over dt equals to w over rho v, because cp and cp the same term will cancel off, thus it stays w over rho v ti minus t plus q over rho v cp. This is our equation for the dynamic model. At steady state, it is said that d capital T over dt equals to 0. Thus this differential term will become 0, and w over rho v times ti bar minus t bar plus q over rho vcp, and this is the equation for our steady state.